So this is dark matter. Thank you for the invitation to come and talk to you this afternoon. You can see from the subtitle I'm going to be looking at why it's dark and asking the question, does it matter? So for quite a while now we have known that the universe has a dark side. That's been known for possibly longer than you appreciate. For the last 100 years or so we've known that there's been a problem when we look out into the universe. One way of thinking about it is we have matter, and matter has a mirror image which we call antimatter, and now I'm talking about dark matter. And here in the cartoon, if you can't read it at the bottom there, the professor is saying, after the discovery of antimatter and dark matter, we've just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. Well, we are talking about dark matter, and that does definitely have an influence on the universe, as we'll see in the next few slides. So if we take everything we know about, if we look at all the matter that we can see in the universe, whether that be out in galaxies or here on Earth, if we subdivide all the stuff we know about versus the stuff we don't know about, we find rather embarrassingly that only 60% of all the matter that appears to be in the universe is the stuff that we are familiar with, the stuff that we really do know about. That 16%, if we just take that out to one side for a moment and ask, what is that 16% of all the matter in the universe that we do think we understand? Well, we can subdivide that 16%, and it turns out to be 13% of it is simply gas, mainly hydrogen and helium, and only a tiny amount of it happens to be stars. Only 2% is stars. And there's a tiny little wedge there, which is a particular type of particle, which we'll mention a little later on, called a neutrino. So when you look out into the universe and you see clusters of galaxies and trillions of galaxies, and we know that each galaxy has hundreds of billions of stars in it, you might think that stars make up most of the mass of the universe. But actually, they're only a tiny fraction. In any given galaxy, there's far more gas than there is stars, in the sense that when we work out where all the atoms are, some of the atoms are in stars, most of them have been ripped apart, but most of the stuff is still there. Whereas the gas in between the stars actually accounts for more of the matter that we can actually see. But even all of that only adds up to a small fraction of the total mass that we think is there. So what is this extra 84% of all the matter, which is not simply stars and dust and gas that we can easily see? That's what we're talking about. So I'll start with describing why it's dark, and I'll talk about the interaction between matter and light. And I'll be taking you through a few pieces of the evidence. You can argue that there are 4 pieces of evidence that tell us that dark matter exists. I'm certainly going to have time to touch on the first 3. I might skip the 4th. It'll be in the slides, the handout that I'll make available to you if you want to read about that. But I'll be going certainly through the first 3, looking at galaxies in clusters, looking at stars in galaxies, and thirdly, looking at gravitational lensing. We'll then ask the question, well, okay, if there's evidence that it exists, what actually is it? And there are 2 possible candidates which go under the wonderful name of WIMPs and machos, and we'll look at those 2. And then finally we'll end with, well, so what? Does it actually matter whether or not dark matter exists or not, other than giving you a few esoteric results in some astronomical measurements? Okay, we'll start with why is it dark. So the simple answer as to why dark matter is dark is because it's not light. Okay, that's a little bit fatuous. A more useful answer is, well, dark matter has a certain set of properties. It does not behave the same way as what we will call ordinary matter or normal matter. Normal, ordinary matter, the stuff that you and I are made of, the stuff that stars are made of, the stuff that galaxies are made of, the stuff that we can see in the night sky, that interacts through what we call the electromagnetic force. In other words, ordinary matter emits and absorbs light, and I'm not talking just about visible light, I mean any electromagnetic wave, whether it be gamma rays or X-rays or ultraviolet rays or visible light or infrared light or radio waves. I'm bunching them all together and just referring to them as light. So ordinary matter emits and absorbs electromagnetic waves, i.e. light. And hence we can detect matter through that interaction. We can either see stars shining because those stars are emitting light, or if we hold an object up to a bright object, like when when the moon covers the sun, we see the sunlight is reduced because the moon is absorbing that light. So we know that bright objects like stars can emit light and all other material can absorb light, and sometimes we can see material not because of the light it emits but because of the light it absorbs. So we see some objects that are dark against a lighter background. But regardless of whether it's absorbing or emitting, the interaction of light allows us to detect the existence of matter. Dark matter does none of that. Dark matter does not emit light. Dark matter does not absorb light. So it's a little bit of a misnomer, because if you see a large dark cloud in the sky that's absorbing the light from more background stars, you might think, oh, is that dark matter? No, dark matter doesn't absorb light. So a better description of it would actually be transparent matter. But that's a rather awkward phrase, and that hasn't caught on, so we're stuck with the name dark matter. Everything that we see around us, everything that we are made of, for instance, we're made of molecules which are made of atoms, and atoms can absorb or emit light. And that's because of the behaviour of these electrons that are buzzing around the nucleus. A positively charged nucleus in the centre there, and a whole load of negatively charged electrons buzzing around, like bees in a beehive perhaps. And it's the way they interact, the way the electrons can change their energy, that tell us about how atoms can absorb light and how they can emit light. So dark matter must be something else. Dark matter is nothing to do with atoms, because we understand atoms and we understand light and we understand the interaction between atoms and light, how atoms generate light, how atoms absorb light. Dark matter must be fundamentally something else. So let's think about what the evidence is that the dark matter exists. Let's think first about galaxies in clusters. We can ask the question, what is it that holds galaxies together in a cluster? If we look out, ignore the star at the top of the image, if we're just looking at all of the various galaxies in this particular image, we have a lot of galaxies, maybe a few dozen, maybe a few hundred galaxies, that all seem to be in the same part of the sky, and as far as we can tell, they all seem to be bound to each other. In other words, they would simply drift apart if it wasn't for gravity holding them together. So what holds galaxies together? Yes, it's gravity. It's not a trick question. It's gravity that's keeping all of these clusters together. If gravity didn't do that, these would simply drift apart. Gravity, of course, depends on mass. And if we ask the question, well, how much does that cluster weigh? What is the total mass of all of the galaxies in that cluster? Well, it's a little bit tricky to work out, but there is a process we can go through to get an estimate of how much mass there must be in that cluster. We can estimate it from how bright the galaxies look. We can estimate it from the luminosity of all the galaxies in the cluster. So we can measure the galaxy brightness, literally just measure how much light is arriving at Earth from that particular galaxy, and work out how much light must be radiating in all directions, assuming we know how far away this galaxy cluster is. And if we've got a reasonably good understanding of how stars work, and let's assume that we do for the sake of argument, we understand how stars are born, we understand how stars evolve, we understand how stars die, and we've got a pretty good idea of how much light we would expect a star to generate during its lifetime. Therefore, if we can measure the galaxy brightness, then we have an estimate of how many stars must be producing that amount of light. I've said roughly there because we can't pin it down to 3 decimal places, but we do know it to perhaps within a few percent or so. And if we know how many stars are there, then we've got an estimate of the mass of all the stars. Again, based on our understanding that some stars are a little bit lighter than our sun, some stars are a little bit heavier than our sun. But if we know about how stars are evolving in any given galaxy, we can get an estimate of, if we know roughly how many stars are there producing all of this light, we can get an estimate of how many there are and hence the total mass of all the stars. And hence we can get an estimate of the mass of any given galaxy based on its brightness. And we can do that for all of the galaxies in the cluster if we want to know, roughly speaking, the total mass of everything that's shining inside that cluster. So if we do it for all the galaxies, we get an estimate of the total mass of the cluster. And then we can ask, well, given that we know how gravity works, if we know how massive the cluster is, how strong would the gravity be that's keeping this cluster together? And when we work out how strong the gravity is that's keeping this cluster together, it's been known for quite a while that there's a problem. As early as the 1930s, nearly a century ago, it was realized that if you calculate the total mass of a cluster and calculate the gravity in this way, the total gravity you calculate is not enough to keep the cluster together. The galaxies should have drifted away a long, long time ago. There's no reason to suspect that any picture we take of a cluster is taken at a particularly special time when the galaxies happen to be close to each other. If we see clusters everywhere, then presumably there are clusters because gravity is holding them together. And yet, when we calculate how strong is the gravity, it's not strong enough to keep the cluster intact. Something is definitely wrong. It's as if calculating how much mass do we have based on all the things that are shining, all the stars in the galaxies. Using the luminosity to estimate the mass underestimates what must be the true mass, not just by a few percent, not by 10%, not by 50%, but by a huge factor. A factor of 2 or 5 or 10. There's as if there's some additional mass. This phrase will turn up more than once in this talk. It's as if there is something else out there. There is some additional mass that is not luminous because we've taken into account all the mass that's luminous, all of the stars. It's as if there's something else out there that's providing the extra gravity that is keeping all of these galaxies in this cluster. It's binding all of these galaxies together. It's not luminous mass, it is something else. Let's call it dark matter. That sounds pretty cool. In the early days, this problem was simply called the missing mass problem because it was realized that adding up stars doesn't give you the whole picture. But these days we talk about the missing mass, we've given it the label dark matter. Something is out there that is providing this additional gravity. Let's take a second piece of evidence, and now we're going to look not at galaxies within a cluster of galaxies, we're coming down in scale and asking the question about stars within a galaxy. I've said all galaxies rotate, arguably most galaxies rotate in the sense, and all spiral galaxies rotate in the sense that we're used to, in the sense that if we look at a galaxy, it appears to be rotating and the stars appear to be moving around the centre of the galaxy. We can ask the question, how fast are the stars moving? And we can get an estimate of this from the Doppler effect. Perhaps you're familiar with this. If we look at the spectrum from a star, it usually has characteristic absorption lines corresponding to particular elements in the atmosphere of the star. And if they are unshifted relative to the positions of those lines in a spectrum that we can measure in the laboratory, that means the star is neither coming towards us nor going away from us. But if the star is moving away from us, those lines will appear to be shifted to the red end of the spectrum, and we call that a redshift. If the star is moving towards us, those lines get shifted in the spectrum towards the blue end of the spectrum, and we call that blue shifted. It's analogous to the change in pitch that you would hear in a sound, for instance, in a ambulance siren that's going towards you and then away from you. That sudden change in pitch as it passes you is analogous to what we're seeing in the Doppler effect of absorption lines in a spectrum. So even though we can't necessarily make out individual stars, if stars are moving collectively in a particular way around a galaxy, we can start to get an idea of how that galaxy is rotating and how the stars are moving by looking at the spectra of those stars and making a note of where those absorption lines are. So for instance, if we use the idea of a disk-type galaxy, if the galaxy is rotating, then some of the stars will be moving around the center of the galaxy and some will be moving towards us at any given point and some will be moving away from us. And so we can use the Doppler shift in this particular graphic on the right. You can see that if the stars on the left, as indicated by A, if they happen to be moving towards us, we would expect their spectra to be blue shifted, whereas on the right, the stars moving away at the point C would be red shifted. And those at the point B would be moving perhaps sideways and they would not give a Doppler shift. So we can do that for galaxies. We wouldn't necessarily choose a galaxy like this. Because we're looking at the galaxy effectively face on, all the stars would be rotating around the center of the galaxy, but none of them would be coming towards us or coming away from us, and therefore they wouldn't have any significant redshift or blue shift. So we wouldn't choose a face-on galaxy. Neither would we choose a galaxy which, instead of being face-on, was virtually edge-on. Now, there we will have stars moving away from us and other stars moving towards us, depending on which way this galaxy happens to be spinning. But you can see down the middle of this galaxy, as is common with a lot of spiral disk galaxies, there's a lot of dust there. And so that dust will make it difficult to see what the stars are actually doing. So directly edge-on is not great either. So we would choose something in between. We would choose a spiral galaxy in which we can see that there's a certain rotation. We can't actually tell which way round this galaxy is. We can't tell if the rotation is clockwise or anti-clockwise as we look at it here, in the sense that we can't tell whether or not the stars at the top will be necessarily coming towards us or whether it's the ones at the bottom that are coming towards us, because we can't tell which way round this galaxy actually is. But by looking at the spectra, these are not the actual colours of the stars. This is just a schematic telling us that if the stars at the top happen to be going away from us in this particular spiral galaxy, they will tend to be blue shifted. And if the stars at the bottom of this image happen to be if the stars at the top are coming towards us, they'll be blue shifted. If the stars at the bottom are moving away from us, they'll be red shifted. And the stars near the middle will perhaps be neither blue nor red shifted. So that's just a schematic. But because the amount of the shift will tell us how fast the star is moving, we have a way of basically at any point within the galaxy measuring how fast the stars are moving around the centre of the galaxy. And that is key for determining the existence of dark matter. What do we expect to see? If we say, well, let's look at stars at different distances from the centre of the galaxy, what would we expect to see for orbital velocity? How should it vary for different stars at different distances from the centre of the galaxy? If we think about our solar system, that's not quite the right sort of model to use, because in our solar system, most of the mass of the solar system is in the sun and the planets are going around the sun. It's not quite the same as stars going round other stars in a galaxy. But if we think about the solar system for a minute, we can measure the speed of the various objects in the solar system, such as Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc. And we can plot their velocity in kilometers per second as a function of how far away they are from the sun. And we see this characteristic curve. Mercury is very close to the sun, so it has to move very fast to stay in its orbit. Uranus and Neptune are much further from the sun, so they can go at a much more leisurely pace to stay in their orbits. Sometimes you might see this same figure, but instead of being plotted on a vertical scale, which is just 0, 10, 20, 30, 40, you could plot it on a logarithmic scales, and then you see that the relationship between velocity and distance is a straight line. But we're going to stick to the idea that we're just going to look at this curve. So the further away we get from the object that is keeping us in orbit, then the slower the orbital speed we would expect to be. That's the take-home message from how we look at planets in the solar system. The further we are from the centre that's keeping us in orbit, the slower we ought to be moving. So we can ask ourselves, well, what do we actually see if we start to look at the speed of stars? In this particular case, we can calculate from the spectra how fast a star is moving as a function of distance from the centre of the galaxy, and you can see we're moving out 10,000 or 20,000 or 30,000 light years in this particular set of observations. If we look at the stars that are fairly close to the centre of the galaxy, remember stars in this sort of region are going to be pulled towards the centre, but remember there's lots of other stars around them as well. So we can't imagine that all of the mass of this galaxy is concentrated at the centre. There might be a big black hole there, but most of the mass is not necessarily concentrated in the middle. So when we look at the speed of stars, in other words, if we look at stars as a function of distance, we find their velocity increases simply because most of the mass is contained within a particular region. We can think of most of the mass of the galaxy as being within that red ellipse, simply from looking at where the luminous stars are. Perhaps 99% of the galaxy is inside that ellipse. So any star that's orbiting inside there will be orbiting around a smaller number of stars. But once we get beyond that red ellipse, once we get to 15 or 20 or 25,000 light years, we're now outside most of the stars in the galaxy. We now should be in a position a bit like the solar system, where all of the planets are quite a long way from the most concentrated mass in the middle, which would be the sun in our solar system. But now, once we are at 20 or 25 or 30,000 light years, now we can regard the galaxy as being there in the middle in the system, and so the speed at which the stars should be rotating around the galaxy when we get further and further away should start to decrease, just like in that pattern that we saw in the solar system. So we would expect the speed of stars to come down as we get further and further away, as indicated by that dotted line. So the key thing is, what do we actually see when we look at stars further and further and further away from the centre of the galaxy? Well, unfortunately, it starts to get rather difficult to find enough stars, simply because most of the stars are inside the ellipse there that we've shown. Most of the stars are inside that region, and so there are very few stars to pick to measure their speed to see what's going on. Fortunately, there's lots of hydrogen gas around, and so we don't need to choose stars. We could just choose atoms or molecules of hydrogen. It doesn't matter what the mass of the object is, the speed should be the same if they are orbiting at that particular distance from the centre of the galaxy. So we're going to switch from measuring starlight to measuring the speed of hydrogen gas. But still the same would apply if that is all of the mass in the galaxy. If what we can see is all there is, we would expect that curve to start to come down. What do we actually see? Nope, it keeps going up and up and up. The hydrogen that's a long way from the centre of the galaxy appears to be moving really fast, much faster than we would expect if it's being kept in orbit around the galaxy by the mass that we can see in all the stars. So again, how do we explain the fact that there's so much gas that's moving relatively fast? We would expect it to be 2 or 3 times slower at that distance, as indicated by the dotted line. Something is keeping the stars and the hydrogen going quite fast, even a long way from the edge of a galaxy. There's the phrase yet again. It's as if there is some additional mass that is not luminous, that is providing the extra gravity that is needed to keep the stars, or the gas, orbiting at high velocities, even a long way outside the visible edge of the galaxy. When we take all the stars into account, it's not enough to account for that particular observation of the velocity not falling the way we would expect at large radii. So, perhaps dark matter again. A second piece of evidence, independent of the first, that implies something is out there that is not visible but is still having a gravitational influence. If we see what that would look like, we can't usually watch galaxies rotate, so we can just imagine in a simulation what would the rotation of a galaxy look like if there was no dark matter. Here, the velocity in the centre, around close to the middle of the galaxy, is quite fast, and the stars towards the edge, the outer edge of the galaxy, are moving quite slowly. If you have a look at some of these stars on the edge there, they're moving quite slowly. There's a little glitch every once in a while when the video simply resets itself. And at the bottom there you see a schematic of the velocity falling as a function of distance from the centre of the galaxy. But that's not what we observe. When we measure star velocities, we much more likely find something like what's going on the right. The same high speeds in the middle there, but notice now that the stars on the outer part of the galaxy are also moving quite fast compared to what we would expect on the left-hand side. And the so-called rotation curve, the velocity as a function of distance, in this particular case is quite flat. It's not falling off as we would expect. For some galaxies it's quite flat, for some galaxies it goes up, but for a lot of galaxies it does not come down at the rate we would expect if the galaxy only contained the sort of matter that we can see because of the stars shining. Virtually all the galaxies that we look at seem to have some missing mass. It's as if there is some dark matter in every galaxy we look at. In some cases, the amount of dark matter is much, much, much larger than the amount of matter that we can account for simply by looking at the stars. Let's have a look at a third piece of evidence that dark matter exists. So-called gravitational lensing. This one is unlike the previous two pieces of evidence. We can calculate the existence of mass, or the amount of matter that exists, from its gravitational effect. Not on galaxies in a cluster or stars in a galaxy, which was the previous two examples we've given, but the gravitational effect on light itself. Yes, I know that I've said dark matter does not interact with light. I agree with that, yes. But if it has matter, if it has mass, although dark matter doesn't emit or absorb light, if it has mass, then it has a gravitational influence on other bodies, and it has a gravitational influence on light itself. In other words, dark matter can bend light. It can't interact with it in the sense it can't generate light, it can't absorb light, but it can make light beams bend as it passes dark matter. So there's a little picture of what we're talking about. Let's imagine that we have a distant galaxy here, which is actually quite small, and we here on Earth are looking at the light produced from this distant galaxy. But the light hasn't simply moved in a straight line in order to reach us, because there's a lot of matter here. Let's imagine there's a large galaxy cluster in between this distant galaxy and the Earth. And that large amount of mass there distorts space, or if you prefer, it simply bends the light, because matter produces a gravitational influence which makes light bend, just like light will bend as it grazes the surface of the sun, as was demonstrated during an eclipse in the early days of Einstein's general relativity floating around. That was an observation that convinced us that we have a reasonable understanding of how gravity works. So we can either think of mass distorting space and then the light follows the curvature of space, or we can simply imagine the large mass represented by this galaxy cluster, and we could just think of it as a large gravitating body which makes the light bend, because a large mass will make light bend. So instead of seeing simply a galaxy in the distance that might look like that, we see it as a rather distorted image, because the lens is not perfect. This is not the sort of lens that you would have in a camera, or we're not talking about the sort of optics that we have in a telescope. The mass is going to bend the light in a rather distorted way and give rise to rather distorted images of a more distant galaxy. But we can do the same trick that we did with thinking about stars moving in a galaxy. We can ask, how much mass would we need to make the light bend in the way it does? We can see here that we've got a distant galaxy. We can't see the galaxy itself because the galaxy is, if you like, hiding behind this rather orangey one. So somewhere in the very far distance there's a blue galaxy, and the light from that blue galaxy is being distorted on its way towards us, just like we saw in the previous picture, and it's being distorted into this horseshoe. It's not simply giving us a slightly distorted image of that galaxy, it's producing a very distorted image of that distant galaxy. How can we think about getting distortions which end up looking like a horseshoe or maybe nearly a circle? Well, we can imagine what's going on. Instead of thinking about a galaxy cluster having mass that bends light, let's just think of another lens which is rather imperfect. Not the sort of lens that we would have in a camera lens. Let's think of the bottom of a wine glass. There, the glass is of different thicknesses, thick near the stem and a little thinner towards the base. But if we imagine light travelling through the base of a wine glass, there's a candle in the distance there in the top left. And in the top right, you can see if we were to hold up a wine glass in front of that candle, the candle now distorts to the point where it's now what? 1, 2, 3 bright blobs rather than just a single image. And that's the distortion produced by that particular rather imperfect lens. And if we hold the wine glass in just the right angle, we might get what we've got in the bottom left there, where the candle flame might actually distort to the point where it appears as a complete circle. Or in the bottom right there, we see it produces rather large arcs, sometimes 2 arcs on either side of the lens itself. So we can get a lot of different distortions depending on what the mass is in the galaxy cluster, what is the mass of the glass in this case, and what angle it is, how it's arranged in space relative to the distant light. So we can get lots of different types of distortion. But the key thing is that if we look at what distortion we get, if we look at distant galaxies and we say, well, there seems to be a galaxy here, but there's a little bit of a distortion here, and there's a very distorted galaxy down the bottom here, this long thin arc, and there's another arc here, and you can see other arcs in different places. So there are clearly galaxies in the distance there being distorted by this collection of rather yellowish galaxies, which we interpret as being in the foreground of these more distant galaxies. The distorted images allow us to calculate the mass in the lens. It's not a very easy calculation to do, but it can be done. If this is the distortion we see, what matter must be there, what distortions of space are being produced by this matter in order to make the light bend the way it does. A tricky calculation, but theorists can do this. If we understand Einstein's theory of general relativity, we can calculate for a given distribution of mass how that distorts space, and hence how that distorts light travelling from a distant object to us. So if we look at lots of examples of this, we can see, okay, I can see the distortion, I can calculate the mass. What we find is that that mass that's necessary to distort the light the way it does is more than we can account for by counting up all of the stars that we can see in the galaxy cluster. Just as before, we can estimate how big is that galaxy cluster by looking at how bright the galaxies are. But when we compare that with the mass that we would need to distort the images, we find they don't tally. We need more than we can account for just from looking at the luminous mass of the cluster. Here we go again. It's as if there is some additional mass that is not luminous because it's not accounted for by looking at the stars. Something else is providing the extra gravity that's needed to bend the light and distort the images in the way that these do. So a third strand of evidence that dark matter exists, and this one is completely independent via a completely different route compared to the other two. I'm not going to mention the fourth element of other evidence about the cosmic microwave background, but there's a note of that in the handout if you want to go and read about that. I'm going to jump forward and say, right, yes, okay, fine, there is lots of evidence for dark matter. 1, 2, 3, and a fourth one as well. So, right, there is definitely evidence that something is out there. other than stars and gas and dust and everything that we can account for. But what is it? Right. There are two candidates for what I'm going to label now DM rather than continually write out dark matter. There were two main candidates, and rather whimsically they're known by the acronyms of MACHOs, which are Massive Astrophysical Compact Halo Objects, a bit of a mouthful, and WIMPs, which are Weakly Interacting Massive Particles. WIMPs actually came first, but a number of physicists said, well, I'm not going to work on WIMPs, that's not a very masculine sort of thing to do. I'm going to work on something which is altogether more masculine. Yes, I'm going to work on machos. And then they sort of reverse engineered, okay, if we're going to work on machos, let's find a nice way of describing them. So I'm going to look at both of those and ask, are these an explanation for dark matter? So let's start with machos. Massive astrophysical compact halo objects. Object, well, that doesn't mean anything, that just means something. Massive, well, these things have to be massive in order to account for the total mass that we're looking for. Remember, there's more dark matter than there is ordinary matter, so whatever these things are that are accounting for the dark matter, they must be fairly massive objects. Astrophysical, well, that sort of means nothing other than we can find them via astronomical means. So what do we mean by a compact halo object? Well, a halo is just the region of a galaxy. A typical spiral galaxy, for instance, might be a bulge in the middle, and then there might be spiral arms and a whole load of dust as well. But outside that region, there's a large spherical region which we call the halo of the galaxy. So the question is, are there lots of compact objects in the halo of a given galaxy? And compact here means small enough that we wouldn't necessarily expect to see them via any other means. So a typical compact object, for instance, might be a black hole. Is it possible that these compact objects are composed of normal matter, but they simply don't emit light? In other words, there's nothing particularly unusual about them other than they are not very luminous. Black holes are a classic example. When you generate a black hole, no light can escape from a black hole. So maybe, is it possible that there are lots of black holes floating around and they can account for the amount of dark matter we're looking for? What about neutron stars and white dwarf stars? That might seem a little bit paradoxical. Surely a white dwarf is white and so will shine. Well, true, a white dwarf after it's been created will be white hot and hence will be radiating a lot of visible light. But a white dwarf is not using nuclear fusion to generate any energy, it's just a hot object which is sitting there and slowly cooling down. So if you wait long enough, a white dwarf will eventually disappear in the sense that its radiation in the visible part of the spectrum will simply fade away as it cools off. So maybe if we've got a lot of very old white dwarfs, they are no longer luminous, and so just like black holes, they would be massive objects. They would be quite compact. White dwarfs and neutron stars and black holes are all very compact. Maybe they exist in the halo of a galaxy, and maybe they are massive enough to account for dark matter. So that's what's meant by a macho. So if we're not going to see them by looking for the light that they emit, how can they be detected? Well, we can come back to the third piece of evidence for dark matter, the idea that matter, whether it's ordinary matter or dark matter, can bend light. So we can look at gravitational lensing, or in this case, gravitational microlensing. We can ask ourselves, well, do we ever see this situation? Is it ever possible that a distant star which we see from Earth, if a black hole or a neutron star or a white dwarf star happens to drift into our line of sight between us and a more distant star, then presumably that massive object will bend light just as more massive objects would do, like a supercluster of galaxies. A small object would also bend light if it's compact enough, like a black hole or a neutron star. So maybe if there are lots of black holes around out there, if one of them happened to drift in front of a distant star, we would temporarily see that star get a little bit brighter because of the focusing effect of that black hole. And then that black hole would drift away and then the star would go back to normal. So if we watch enough stars all of the time, not just pick one or two, but if we pick a few million stars and we watch them all very carefully, would we expect to see any signs of a white dwarf or a black hole or a neutron star that happen to drift in front of them and hence change their brightness? If there's lots of black holes out there, then it's going to be more likely that we see that, compared to if there's very few black holes out there, then that would be quite a rare event. So this was carried out as an experiment. This is an idea of what the Milky Way looks like. This is a picture from inside the Milky Way. That's what we see when we look at the Milky Way in our night sky. But imagine that we've just taken the galaxy and we've just stepped outside for a moment and we're looking at the disk galaxy from the edge. Those two blobs in the bottom right there are the Magellanic Clouds. And we are sitting in the disk of the galaxy. So what we could do, if we think that the halo of the galaxy is full of black holes all over the place, what we could do is sit and watch stars that are in the Magellanic Clouds. So in other words, we could photograph the Magellanic Clouds and do that continuously and watch all of the stars in the Magellanic Cloud and see if any of them suddenly brighten in a way that's consistent with the fact that a black hole might have drifted in between us and the large Magellanic Cloud. So that is what has been done. An experiment was carried out over a period of a few years, watching stars in the Magellanic Clouds to see if there's any sign of the intervening space being peppered with black holes or any other objects, any other so-called massive compact halo objects. And the answer is, well, there are a few of them out there, but there's not enough to account for what we know is the budget of dark matter. Yes, there are a few machos out there. There are a few black holes drifting around in the halo of our galaxy and probably a lot of other galaxies. But when you add up all of the mass that appears to be there, machos can only account for 1 or 2% of everything that we need to account for dark matter. So machos do not appear to be the answer for what is dark matter. So then we come to WIMPs, weakly interacting massive particles. In other words, we're not talking about astronomical objects now. We're talking about maybe there's a particle that we've missed. We are made of atoms, and atoms are made of protons and neutrons and electrons, and we know those protons and neutrons are made of quarks. So we know that us and the Earth and the Sun and pretty much everything else we see in terms of the stars and the galaxies, we know that they are made of a particular group of particles, which we can bunch together and just say, well, there's a mixture of quarks and electrons that account for most of what we can see. But maybe there's some other particles which we've missed, particles that are rather difficult to detect. And they are massive, in other words, they must be massive in order to account for the amount of dark matter we're looking for. What do we mean by weakly interacting? Well, we mean they don't interact with light the same way that the particles in our bodies do, and the particles in the sun do, and the particles in the other galaxies do. So we know ordinary matter interacts with light. Maybe there are some particles which don't interact through the electromagnetic force and hence don't care about the existence of light. They interact through gravity. A particle has mass and that mass will influence other particles through gravity, but they won't interact with each other or with any other particles through the electromagnetic force. There are some particles like that. That's similar to the particle that we called a neutrino, but neutrinos don't seem to have enough mass to account for all the dark matter. So there must be something else. In the particle zoo that we think we understand, there must be something that we are missing, that we haven't seen yet. They were presumably born in the Big Bang, because the Big Bang was the beginning of everything, so dark matter must have been made at the same time that everything else was made. So these weakly interacting massive particles, if they exist, must also have been born in the Big Bang. And just like we know that matter has a mirror of itself called antimatter, for every electron there's another particle called an anti-electron, looks very similar but has the opposite electrical charge, and a proton has an antiparticle called an antiproton, etc. So presumably every particle of dark matter also has an antiparticle which we would call what would we call it, an anti-dark matter particle? Or would we call it a dark antimatter? Oh, well, okay, let's call it an anti-dark matter particle. But we see no strong evidence for dark matter and anti-dark matter annihilating, because if they annihilated much the same way that a proton would annihilate with an antiproton, or an electron would annihilate with an anti-electron if they came into contact, there's now apparently very little evidence for dark matter annihilating with anti-dark matter. It's now rather rare. But maybe we should be looking in the places where it's most likely to happen. A bit like if you lose your keys, where do you look for your keys on a night? Well, you look under a street light, not because that's where they're most likely to be, but that's where you're most likely to see them if they exist. If they're in the dark, you're not going to find them. If they're under a street light, you might find them, so that's where you should be looking. And it's possible that WIMPs have been captured by the sun, simply because the sun is a very large gravitating body, and these objects don't care about the light produced from the sun, but the sun is a large mass, and maybe these WIMPs would be attracted to this large mass, so maybe there are a lot of WIMPs in the sun. And maybe they might be annihilating, the particles might be annihilating with antiparticles, and they would produce signature particles which we think would be neutrinos. So if we look for neutrinos, maybe we would be looking for a signal of dark matter particles in the sun. How on earth do we look for neutrinos, which are elementary particles which travel close to the speed of light and have very little mass, but they are moving very quickly? Well, it's possible to detect these very energetic particles using a large tank of water. Doesn't sound very sensible, but that's how it could be done. There's an analogy to particles travelling through the air. For instance, if we have a jet fighter moving through the air faster than sound, what actually happens? Because the aircraft is travelling through air faster than sound can travel through air, what happens? It sets up a shock wave. We would call it a sonic boom. Well, there's an analogy for what would happen if a particle is moving through a medium faster than light can travel through that same medium. It's an analogue of a sonic boom, and it's called Cherenkov radiation. So instead of listening for a sonic boom telling us, we've just heard something that's travelling faster than sound, we can look for the distinctive characteristics of Cherenkov radiation that tell us, a particle is now moving through the medium that we're looking at faster than light can travel through that medium. And that's why when you look at, for instance, a nuclear reactor, it seems to be glowing blue. It's not because Hollywood think that's look really cool and wouldn't it be nice if we could make this glow blue. No, that's what it actually looks like. Because if you surround a nuclear reactor with water, then very energetic particles from the reactor can travel through the water faster than light can travel through the water. Yes, nothing can travel faster than light through free space, but through water, light has got a particular speed, and when you work out how fast these particles are moving, if they are going faster than light can travel through the water, then you get this optical equivalent of a sonic boom, which is Cherenkov radiation, which is characteristically blue. I'm not going to say why that you tend to get blue light rather than any other colour, but a flash of blue light is an indication that a particle has gone through your medium, in this case water, faster than light can travel. So if you have a large tank of water and a very energetic particle goes through that tank of water, it produces a blue flash of Cherenkov radiation. And if you have light detectors, photodetectors, all around that large water tank, then you can see the blue flash, and if you have lots of detectors, you can figure out where that particle must have come from in order to produce the flash, which tends to flash in the direction it's travelling. So in this particular case, a whole load of detectors would record the blue flash over here, and a whole load of detectors on the other side probably wouldn't. So that gives you an idea of where it's coming from. And if you know where it's coming from, you can say, did that very energetic particle come from the sun, or did it come from somewhere else? And just to give you an idea of size, if you take the water level down a bit and you look at the individual photodetectors, of which there are a very large number, you can see here, if you're having a difficulty getting the scale, just bear in mind that right in the centre of the image there, that's two people in a dinghy. That tells you the scale of this water tank, and it gives you an idea of just how many photodetectors there are in this huge volume. So that is an experiment that is effectively ongoing. These are these photodetectors. I'm not sure quite how large they are, about the size of a football or something like that. And there are a very large number of them in the experiment I was just showing you. But there are other experiments going on at the same time. That one in Japan is not the only one by any means. There is also the idea of using not a very large volume of water. There's no particular reason why water is chosen other than it's cheap. But there's an alternative. Why not go to the South Pole and use frozen water, i.e. the ice? So here we have a laboratory sitting on top of the ice cap. But that's not where you're detecting the particles. You're actually detecting the particles going through the ice way underneath the ice cap. The ice is about 2.5 kilometers thick in the South Pole, in Antarctica. So if you have these detectors, these little footballs, and you put them like a string of pearls through a lot of individual strands here, you can end up filling a volume which is something like 1 kilometer by 1 kilometer by 1 kilometer. You're looking at a volume which is 1 cubic kilometre of ice. And just to put that into scale, there's the Eiffel Tower on the same scale there. So instead of using a large man-made water tank, here you're using the ice, and any particle travelling through the ice faster than light can travel will produce a blue flash, which is then picked up. So you can use the same sort of idea, and different detectors around the world are all doing the same sort of thing, looking for these flashes, trying to work out if we're picking up particularly energetic particles from the sun that would indicate the existence of dark matter concentrated in the sun. As well as being concentrated in the sun, some people are also thinking on a slightly larger scale and saying, well, if WIMPs do exist and they tend to want to congregate where there's a large mass, yes, they might congregate in the sun simply because they are gravitationally attracted to the sun. But where else do we know of a very large mass that exists in a small region of space? Well, there might be an awful lot of them in the centre of the Milky Way, where there is a supermassive black hole. Perhaps a lot of them are in the neighbourhood of the centre of the galaxy, and we might be able to detect their existence. It is thought that if dark matter particles exist in the centre of the galaxy, it is thought that annihilation of dark matter with anti-dark matter might produce some very energetic gamma rays, very energetic electromagnetic radiation. So as well as detecting very fast particles moving through water or ice, there are also plans for experiments to look for very energetic gamma rays arriving here on Earth. So again, if we're thinking about the centre of the Milky Way, again, this is a picture from inside the Milky Way, but let's remind ourselves that the centre of the galaxy, where the bulge, if you like, of the Milky Way galaxy exists, that occurs in the constellation of Sagittarius, which is, unfortunately for us, in the southern celestial hemisphere. So England is not particularly well suited for looking at what's going on in the centre of the galaxy, and so experiments in the southern hemisphere are being set up. So one such experiment is the Cherenkov telescope array. An array of telescopes, where would you put these? Well, contrary to the picture here, you wouldn't put them in the deserts of North America. This seems to be Monument Valley, according to the picture in the background. You would actually put these, for instance, in the high Andes, where you've got relatively stable atmospheric conditions, and you can look into the sky. You're not looking into the sky in the direction of the centre of the Milky Way. You're using the Earth's atmosphere as the detector. Just like the water tank or the ice cube were the detector, we're now looking for very energetic rays coming into the Earth's atmosphere and producing a shower of particles that are moving so fast, because they're so energetic, that they could be moving faster than light can travel through the air. And so again, you get a flash of Cherenkov radiation. And you can see that a number of different telescopes might be able to detect the flash. Remember, although the air is relatively low density, there's an awful lot of atmosphere up there that you can see by pointing telescopes into the sky, and therefore you've got a very large volume to explore, and you've got lots of telescopes that might see the same blue flash. And by taking the data from lots of telescopes, you can figure out whether this particle that produced the gamma ray that produced all of these particles, whether that was coming from the direction of the center of the galaxy or not. So there's lots of these types of experiments that are indirectly looking for the signature of dark matter. There are other more small local ways of detecting dark matter. I'm not going to go through the details, but various people are setting up the equivalent of tabletop experiments, experiments that are on a much smaller scale than the ones I've shown in terms of water tanks or ice cube or Cherenkov telescopes looking at the atmosphere. There are some ways that people are trying to look directly for the influence of a dark matter particle interacting with their experiments. And this is going on in Italy and Canada and France and elsewhere. So there's a number of experiments there. I haven't listed them all. I've just given you a few acronyms. If you wish, you can go and look them up and see what these various experiments are doing. Some of these experiments have been running for a few years and have observed a few blips indicating they might have seen a dark matter particle passing through their experiment, but most of the results so far have been contradictory and nothing yet has been confirmed from any of these Earth-based experiments. Let's just finish by thinking about an alternative. Maybe we have misunderstood how gravity actually works. Maybe we only seem to need dark matter because when we work out how stars are being held in their orbits around a galaxy or how galaxies are being held in clusters, maybe we only seem to need dark matter because we've got gravity wrong in the first place. Maybe gravity isn't universal. Maybe gravity works differently on different scales. Maybe the gravity of how a supercluster works is not the same as the gravity as how stars move within a galaxy. Maybe that's different from how gravity works on a scale of the Earth going around the Sun, or how on Earth two masses might attract each other through the force of gravity. Maybe the scale that we're looking at makes a difference. And there is a theory called modified Newtonian dynamics, or MOND, in which effectively you build that into the theory. Rather than assuming gravity is universal, let's build a theory in which gravity works differently depending on the scale that we're looking at. Depending on how you build that theory, you can get rid of the need for dark matter. The problem is you solve that problem and you introduce a dozen new problems. So it's not yet at the point where people can say, yep, dark matter doesn't exist because all we need to do is to tweak gravity and we've got a solution. Yes, we can tweak gravity and we can claim that we've got gravity wrong, but until we can get rid of all the other problems that are generated by tweaking with gravity, it seems like dark matter is real, dark matter must be there. So let me finish with, does it matter? What are the consequences? Apart from the fact that galaxies rotate at the wrong speed, does that really matter that galaxies are rotating at a speed we wouldn't expect? Well, it really does matter when we start to look at simulations on the grand scale of how the universe came to be. In other words, how we get galaxies and how we get distributions of galaxies, starting with a hot fireball of the Big Bang, and how the universe expands and cools to produce the galaxies that we now see. If those simulations don't include dark matter, we can't get the answers right. In other words, in the very early universe, a fraction of a second after the Big Bang, everything that we now see in the observable universe used to be in a volume that's about the size of a golf ball, thereabouts. And the golf ball had dimples. These dimples are not dimples as in a golf ball, they're dimples in the sense of very small variations in temperature and in density. And those tiny variations in density in the early universe, as the universe expanded and gravity started to do its thing over billions of years, that collapsed into what we now can think of as the cosmic web. If we take a large volume of space and say this is almost uniform, but there are small variations in density, what happens in this simulation if we let gravity do its stuff? We find that the matter starts concentrating into what we can now see of as filaments and voids between the filaments, and we see this web starting to come into existence. And where the filaments cross each other, we get little pockets of very high density. That's where galaxies and clusters of galaxies and superclusters of galaxies start to form. So we can understand how we go from the early universe to a universe full of galaxies by just letting gravity do its stuff. But if the simulation does not include dark matter in the calculations of how matter is behaving, then we can't get the galaxies that we see around us. In a way, you can think of it as it doesn't come together fast enough. Without the dark matter, the universe would eventually clump into galaxies, but it would take far longer than 13.8 billion years, which is our current estimate of the age of the universe. So if we want to go from a Big Bang to the universe that we see now in 13.8 billion years, we can't get the physics right unless dark matter is in the mix. Without dark matter, we would not have the universe that we see. We would not have stars and galaxies in the form we see them today. So absolutely, yes, it does matter. When we look at things on the largest scales, we see the foamy web-like structure of these filaments and these voids. You can see these dark black areas where there doesn't appear to be much matter. We zoom in and we see more and more detail, and where the filaments cross, we see the galaxies and we see the clusters of galaxies. But only if we seed the universe with a large amount of dark matter in the first place. If we only seed it with the amount of matter corresponding to how much we can see in the stars today, we can't get it to work correctly. So here's a little animation just to see how we can tie that together. This is the universe on the largest of scales, billions of light years, and we're now zooming into this cosmic web, this foamy structure, and we're starting to look in more and more detail at a small collection of filaments. There's still a few voids there we can see, but as we zoom in from a scale of billions of light years, now zooming into a scale more like millions rather than billions of light years, now we see where these filaments meet. This is where matter is streaming down these filaments to form the stars and the galaxies and the clusters of galaxies. And these simulations, this particular simulation, is called the Millennium Simulation simply because it was carried out quite a few years ago around the turn of the millennium. And more recent calculations come to the same conclusions, that we can see the right sort of structures when we zoom into these simulations compared to what we see in reality, but only if dark matter is there. And now we're zooming back out to the large-scale structure of the universe, which looks relatively uniform on the largest of scales. So I've been telling you about dark matter, about the interaction between matter and light, and how that dark matter is different from ordinary matter. I've given you 3 out of the 4 pieces of evidence that tell us something is out there. I've told you about the 2 possible candidates. One does not appear to be a viable candidate, so we're left with a particle which we haven't yet discovered that can account for all the dark matter. And without dark matter, we can't understand how the universe came to be the structure that we now see. So does it matter? Well, our existence, in a sense, depends on it. So yes, it does matter. Thank you for listening.